So we have a concrete example of the setup that we saw in the previous video. If you have not watched that video, please go watch MM80 before seeing this one. I've shown in that video how the general solution can be written in terms of a exponentially decaying solution for a semi-infinite cylinder, which this is. A combination of J nu and N nu. In this case, we just have J nu. And linear combination of cosine m phi and sine m phi. I used phi in the previous example. I'm using theta in this example, so I'm going to make that modification. The total solution u for r less than a, theta and z is going to be a linear combination from m equals minus infinity plus infinity, some coefficient cm cosine m theta plus dm sine m theta, and some other constant which I'll call a tilde for now because I want to use a for later, jm kr. The argument is always kr, and then I have e to the minus kz. So that's how the most general solution is going to look. Our entire purpose in this problem is to determine all these unknowns, the coefficients. So the first boundary condition that we have is that at any value of theta and z, at the radius rho equal to a, we have the temperature 0, because I've told you the sides are encased in ice. So it's like a calorimeter. Now, then if you have this boundary condition, let's apply it. M equals minus infinity to plus infinity, cm cosine m theta plus dm sine m theta. I'm going to put r equals a here. am tilde jm ka e to the minus kz. Now how can this be 0? The only way this can be 0 is if jm ka is 0. Or if ka is the jm inverse of 0. So what we're going to do is we're going to call this knmn, and so it's going to be the inverse of the Bessel function. You already know how these Bessel functions look. They look like decaying sine waves at infinity. So the inverse value of the 0 is going to be a multivalued function. It's going to have several roots. So let kmn be the nth solution, nth root of the mth Bessel 0. So that's like a double infinity index, because m goes from minus infinity to plus infinity, and n also, there's an infinite number of them. So you're going to have a fairly complicated situation already. The second boundary condition, BC2, is that the bottom of this, where the hot plate is located, is r theta 0, because z is 0, and that's given as r sine theta. So let's apply this one. That's m equals minus infinity to plus infinity, cm cosine m theta plus dm sine m theta, am tilde jm, and now with our newfound knowledge, I'm going to write this as kmn r. By the regular principles of orthonormality with Fourier series, I'm going to get that CMs are 0, because you can nowhere match sine theta with the cosine. And the only dm that survives is m equals 1, because m equals 1 comes with sine theta, and there's a sine theta to the left. So that makes quick work of it. So what I'm going to do now is d1 is the only one that survives, and I'm going to call d1 times a1 tilde my new constant a. So that's what I've been saving a for. And also I'll write kn1 as simply equal to kn, because of all values of m, the only one that survives is m equals 1. So basically the m quantum number is fixed by what happens in the azimuthal direction. Once you have the azimuthal side taken care of, this double infinity suddenly collapses to just a single infinity. So it's, again, suddenly under control. So the solution now, r less than a theta z, is just a sum from n equals 1 to infinity an j1 knr, because the Bessel zeros only go from 1 to infinity, sine theta e to the minus kz, knz. So now all we have to do is determine this coefficient an, and we are done. Now let me also write what kn is. Kn is equal to 1 over a j1 inverse 0. And you can look this up in various reference books where the values of the Bessel functions are listed. Now there is a property that we need known as the Sturm-Liouville Bessel theorem. The full statement can be found in my notes. But the Sturm-Liouville Bessel theorem states that the integral x1 to x2 of r times j1 squared knr dr is in fact equal to a squared over 2 j2 squared kna. This is 0 to a. So that is the information I get from the Sturm-Liouville Bessel theorem. Once I have that, it's just a simple matter to write down the rest of the problem. So I get u of r theta 0, which is r sine theta, now I'm applying the boundary condition, is equal to sigma n equal to 1 to infinity an j1 knr sine theta. So applying the second boundary condition, I get this. And now I'm going to use the Sturm-Liouville to find an. So what I'll do is I'll multiply both sides by j1. So doing that, I'll get the integral from 0 to a. Actually, I'll multiply both sides by r also, because this requires an r. So r squared j1 knr dr, that's the left hand side, and that's equal to the sum from n equals 1 to infinity, but only the j1 term contributes, so that's a jn, that's still a j1. So that's going to be an integral from 0 to a r times j1 squared knr dr. And by this Sturm-Liouville Bessel theorem, we know this is equal to an a squared over 2 j2 squared kna. This tells us what an is, but it gives us an in terms of an integral. That doesn't look good. So we have to evaluate this integral. We're going to use what's known as the recursion relation to do it. There are several recursion relations for Bessel. The one that we need involves finding the derivative in terms of it's like a ladder operator in quantum mechanics. So that's going to be x nu j nu minus 1. So you find the nth derivative in terms of the nu minus 1th Bessel. Now for x I'm going to put r, and for nu I'm going to put 2. So this gives me exactly what I need, tailor-made for my situation. So The reason I did this is because I actually want the integral. So if I integrate both sides, I'm going to get the integral from 0 to a r squared j2 prime dr equals integral from 0 to a r squared j1 dr. That's what I'm really looking for, because that's what I have. And that's equal to this. Well, the integral of a derivative by the first fundamental theorem of calculus is just the quantity evaluated at the upper limit. So the integral from 0 to a r squared j1 k and r dr, the only thing you have to be careful of is the argument is k and r. So when you do the first fundamental theorem of calculus, you have to divide this. So you can also do a change of variables if you like at this point. But you'll end up getting a squared over k sub n j2 k and a. That still may not console you enough, because j is a strange creature, but it can be looked up. Now that we have this integral, we can put this equal to that. So let me do that one step. The left side is a squared I'll just write the answer. It's an equals 2 over jn ka, j2 k and a. And so the full solution, which is u r less than a theta z, is going to be the sum from n equals 1 to infinity k sub n 2 sine theta over j2 k n a j1 k n r sine theta e to the minus k n z, with the understanding that j1 k n a is equal to 0. Now this might strike you as a very complicated way of looking at things, but just remember that j is nothing more than sines and cosines, with them going to 0 at r going to infinity. So it's just oscillation, nothing more. So it's oscillation in the r coordinate, it is an oscillation in the theta coordinate, and there's exponential decay. That's all it really is. These things are not that complicated.